Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's my pleasure to introduce Dr. Devin McKenzie. Devin is a colleague of mine at the University of Washington. He's also the Washington Research Foundation Professor of Clean Energy at the University of Washington. He has a joint faculty appointment in both the Material Science and Engineering Department and the Mechanical Engineering Department. Devin has had a rather distinguished career over the last 17 years where he's been a leader, a scientist who goes into the lab, works, and also an entrepreneur in the area of flexible electronics and printable electronics. So Devin actually was the founder of the first flexible/printable electronics company called Plastic Logic in Cambridge, United Kingdom. Currently, apart from being a professor at the University of Washington, he's also the Chief Technology Officer of Imprint Energy, company that develops flexible high-energy batteries. Devin has only 110 patents and a number of publications. He got his bachelor's at MIT and PhD at University of Florida. In 2015, his company was selected to be the top 50 smartest companies by the MIT Technology Review. So with that, I'll stop and let Devin tell us more about printable electronics.
Thank you. It's a pleasure to be here. I'm relatively new to Washington and certainly my first time out on this side of outside of the lake. So I'm going to talk to you today about printed electronics and sort of transition from, touch on a few areas. Of course, the field is, although new, covers many, many areas. But I'd like to kind of introduce the concept of printing and why it's so old and so new, why it's disruptive, both in terms of how we make devices, a sort of disruptive way to make semiconductor, optoelectronic, and energy devices, but also disruptive in the types of form factors of products you can make from this in an economical way. And talk a little bit about also how this relates to advanced manufacturing, which is the reason why I'm here today, the reason why the state of Washington, University of Washington, the governor as well, wanted to bring the university into supporting federal initiatives in advanced manufacturing, and why printing is a significant part of that for high-tech manufacturing future in the United States. And then we'll talk a bit about some interesting form factors and applications, both in terms of the work in the university, but also in Imprint Energy and the startup companies as an entrepreneurial example. And then talk a little bit about sort of the scalable printed electronics lab building at University of Washington and kind of the initiatives there and how that might lead to interactions with industrial partners, which is part of the reason why I came. So, what's old is new. Printing and even some of the printing techniques we use are very, very old concepts. It's sort of debatable who invented it. We're talking about there's some of the Egyptian tomb paintings in sort of 400 AD include printed, basically essentially screen printing as a technology, all the way through to the Polynesian islanders used to use, took banana leaves and rubbed out the soft organic matter and used to use those to print things on fabrics and textiles. And this is in the first millennia AD. And then later the concept is that eventually diffused into Asia and to China, were the first ones to kind of sort of perfect things like silk screen printing and sort of a much higher quality imaging. And then later, that became the basis for the information age was really about printing, Gutenberg, and how we could disseminate information by printing. And then maybe the next significant advance was in the 19th century, in the 1840s, they started roll printing, the roll-to-roll printing. It's a very old idea, but actually kind of a new idea to semiconductor manufacturing, which is even more primitive, essentially, Stone Age lithography. Litho means stone. The way you make semiconductors today and many devices today is a fundamentally energetically and resource wasteful approach. And the only reason you get away with it is because the amount of information you can pack per unit space is so high that you can make it make sense. But fundamentally, it's fundamentally a subtractive process in the sense that you start with some sort of base substrate. You use relatively high energy expense vacuum coating, physical vapor deposition, other deposition processes which require quite high energies and high temperatures. You coat it with variously high engineered polymer, very expensive and usually environmentally unsound photoresists, photoacids and other things. And you pattern that UV light. You throw away most of that. Then you use that to etch in yet another sort of kind of toxic effluent etching process. And then you throw away that mask completely and you end up with your final feature where you've kind of gone through 3 steps of constant removal and disposal of material to get to your final target. And don't say I'm discriminatory. This is what I learned. This is how I started. As a PhD, I was in 3.5 optoelectronics, and I did this, many hours of this. But it was actually through my experience at Cambridge. I went to Cambridge to work on an emerging new field called organic electronics. We were starting to replace silicon and gallium arsenide with organic molecular materials that also behaved as semiconductors. They were really slow, they were really crude, they had short lifetimes, but they had some very, very special properties. The first one that was exciting is they were highly luminescent. Just like laser dyes and organic dyes can be very luminescent, silicon notoriously poor at luminescing. 3.5s, okay, pretty good at luminescing, but very, very expensive and not so easy to make. The other thing that really drove me in interest in these new materials was how you could process them. During my PhD, we were trying to grow gallium nitride. We're trying to grow cubic gallium nitride on silicon 111 surfaces, heteroepitaxy. If you had more than a fraction % mismatch of the crystal lattice between the epitaxial film you're growing in underneath, you would have threading dislocations and an optical disaster and nothing would work. Organic electronics, you completely remove that constraint. You can integrate heterostructures from different electron transports, band energies, conduction band edges, valence band edges can all alternate stacks with no question of heterointegration, no lattice match required. So you could really build these really much more elegant and complex structures very simply from just sequential coating from solution. You can dissolve these molecules into solutions, form inks, and coat them or then print them. And so, printing is, in the essence, is taking this process and turning it into that. We're completely additively, we're taking a material and additively depositing in exactly what we want, where we want, not throwing anything away. And we're using materials that are molecular. Their semiconductor system is already set up. We're not assembling a crystal. The molecular system is already defined by the chemistry. So we don't have to go to 600C, 800C, 1000C to anneal out crystalline defects and all this sort of thing. The semiconducting system is already made in the molecule, and we're just placing it where we want. And so that's really disruptive in terms of how you can make things, the cost you can make things. And we start thinking about things like photovoltaics, the amount of energy it takes to make things. There's another aspect, and so maybe when you first start thinking about, I've got an inkjet printer, I could be printing circuit traces instead of getting a PCB made, deposited, etched, and all this sort of stuff. That immediately jumps to mind as, to me at least, as kind of additive and novel. There's another thing that's almost more significant that's sometimes overlooked, which is how things are really made. So how things are really made, my phone here involves, 50 different companies and vendors. You would think when I got into this, I always thought, well, it's a high-tech industry. There's massive amounts of automation. It's a super high technology, robots and all these great things. It's not how these devices are made anymore. The microprocessors are made a bit like that. These devices are not made like that. Why? Because this device changes. Every 6 months they're making a new one. And although it seems like they make a lot, in terms of mass manufacturing, the actual number of units they make of any particular design is actually not that large. There's a massive amount of manual assembly and integration in this device. That's why they go to the lowest labor markets, is because there's a huge amount of manual assembly, both in the electronic subcomponents and in the integration of those components. And people like Foxconn and Flextronics, they're very good at managing those laborers. That's essentially what they do. They're a contract army, for hire, mercenary for hire, to assemble and integrate components, the sort of silicon components, optoelectronic components, separate. The PCBs are usually actually made somewhere else and brought in. Batteries is a very manual assemble process, and then those get brought in as separate modules. All these things come together and get integrated largely manually, the immense amount of manual assembly by hand, into this integrated, in this case we're talking about flexible electronics, integrated system on flex, combining rigid solid components from many, many different sources. And that's, of course, you think about just all the different specializations here, all the different transport costs of getting all those components here, all to this place, and the amount of manual assembly it takes, and then shipping it from there back to where these things were made in the first place. A lot of energy and a lot of trouble invested. Printing is fundamentally different. Roll printing in its purest form is a continuous web process where you go from stage to stage to stage on a continuous web. And if you're in manufacturing already, especially in semiconductor manufacturing, one of the biggest problems in, say, making LCD displays, a huge fraction of the money and yield loss is not about the individual unit processes. It's about getting this 2 meter by 2 meter piece of glass from one tool to the next. The amount of manual handling, it's not manual anymore, now it's robot handling, but they're literally picking up cassettes of gigantic Boeing pieces of glass, trying to pick those up on various forks and vacuums and get them from tool to tool. That sort of manual handling is actually a very, very significant issue in the throughput of even LCD panels. When you talk about roll to roll, that sort of handling is completely eliminated. There is no interspersing step because it's a continuous web. It goes from maybe an initial surface treatment through, this is a gravure, or it's a flexographic printing station, dry on that, then you go to the next stage, maybe a gravure print here, a drying stage, a next step, drying stage, print some electrodes, drying stage, and then you can actually coat adhesive and laminate and package and build a continuous device, start to finish, with zero manual handling. No one touches this device from start to finish. No robot or no person. So it's fundamentally, and we can integrate lots of different functionality all in the same substrate. So you not only are you doing additive processing, but you're also eliminating that multi-stage integration network to produce this device. Now, in terms of, that presents something interesting and maybe not obvious in terms of labor force. So now that I'm an educator, we worry about educating engineers and what they're going to go into and what's going to happen to the technology base for the United States. And you start looking at printing, and you think printing's cheap, right? Print newspapers, this is old stuff, it's black, it's paper, it's dirty, crank it out. Actually, printing is a very high technology-driven manufacturing. If you look at where the printing industry happens, you look at these are the top 8 companies where the printing happens. You maybe see China here, but China's a very, very big country. But like Japan, United States, Germany, Great Britain, Italy, France, Canada, these are not known as low-cost labor markets to manufacture. And in fact, in my current company, in my entire career in printed electronics, I have never been to China. I've been entirely in Europe, I've been in Scandinavia, and I've been in Japan, the most expensive per capita places to manufacture in the world. In fact, the initial licensees for my company, we had 2 in the batteries, and one's in Denmark and one's in Sweden. You would never expect that, but if you think a little bit about it, it starts to make sense. It's not about manual handling. It's about running in a highly precise automated piece of equipment where it's about process engineering, very tightly controlled process engineering, which domestically in these countries, United States and others, are very good at. And it's about functional materials. It's about very high value add materials and the very controlled use of those. Printing, when you go to Target, they give you the printer, right? $99, you can buy a huge piece of technology. They give you that, why? Because they're going to charge you a lot of money for the inks and paper. That's how they get you. Well, that's true of the printing industry as a whole. It's about it's about those also about those really high functional, high value add materials that really drive the economics of printing. And then lastly, in printing, and certainly in graphics printing, proximity to market is important. You don't want to take it, ship your design somewhere else, have it made somewhere else, and ship it back whenever it's a relatively inexpensive item. If we're going to print Internet of Things labels for every device, and those labels need to be 10 cents, essentially something like that. We don't want to have to ship a 10-cent item all the way from China and back. It doesn't make sense to do that. Also, these things change fast. Just from a time delay, we also don't want that time delay. So that sort of spurred interest from the federal government back in the days of, what was it supposed to be, the Great Recession? I don't know if it really wasn't true in California, and probably not in Washington either. Certainly house prices didn't go down. But during the recession, the Obama administration, they started the stimulus package. And one of the planks of the stimulus package was how to stimulate high-paying, high-technology jobs in the United States. And they developed these, they funded these manufacturing innovation institutes to promote high technology manufacturing that could stay in the US instead of immediately going overseas, which is what's happened in the past. Just so you know, like at the very beginning of this field, we were doing Plastic Logic, my first startup, we were in displays, and there was actually a United States Display Consortium. How many displays are made in the United States right now? Almost none. So it was not a success, but the idea is because that market was not appropriate. That ship had already sailed, and we were too late. But in the printing industry, in the high functional electronic printing industry, we think we're not too late. We're actually right at the forefront of this. Probably in terms of technology advances, it's neck and neck between the US and Europe as to who's leading technology-wise in sort of print electronics. And if you look at, there's 7 of these manufacturing innovation institutes, and that covers all fields, everything from optoelectronics to steel to building buildings. 3 out of the 7 involve printing. Additive manufacturing, this is 3D printing. This is in Detroit. Digital manufacturing and design, how do you sort of related, but related to controlling manufacturing and just-in-time manufacturing, digital manufacturing. And then NextFlex, the Flexible Hybrid Electronics Manufacturing Innovation Institute. And this is the institute that University of Washington is now a part of, and I'm helping lead that connection. And this is about flexible electronics, a significant component of which would be printed. Things like batteries, sensors, interconnects, and things of that sort. Now, get a little bit on the technology side. Talk about what do we mean when we mean printed electronics? There's sort of 2 categories. One is digital, and we have the prime, maybe the prototype or archetype digital printed electronics is inkjet printing. So we always have a feel, drop-on-demand, piezoelectric drop-on-demand inkjet heads, just like your Epson or your Canon inkjet that can sit on your desktop. But instead, it's been modified, MEMS-based heads, all silicon wetted materials, high-temperature materials, so that it's compatible with things like nanoparticle metal-based inks and much higher resolution. Graphic arts resolution, you're talking about sort of 50 micron, 100 micron features, the smallest, and typically bigger. You don't want to make anything smaller than what you can see. It's graphic arts after all. In electronics, we want to push into low micron or even submicron scale imaging. So these are much higher spec. This is, instead of a $99 printer, this is a $25,000 printer. But still, functionally, you feed in data, you feed in image control data, and you can raster and drop on demand digitally print an image. A lot of there was a lot of work in the deposition systems, but a lot of the hard work has focused on the materials development in order to produce materials that end up as a functional. In this case, this is a nanoparticle silver that started off as silver nanoparticles dispersed in an organic solvent, maybe 4 nanometer, 10 nanometer silicon nanocrystallites. Those are now small enough that they're dispersible into a solution like dissolving salt in water. They're so small that the molecular forces can disperse them, and now we can use that as an ink and run it through a printer. Once we get it on the substrate, we dry it, but we don't have a metal yet. We have to sinter that metal and actually grow those crystallites and turn it back into a continuous metal. But with that, that's a lot of engineering over the last 10 years has gone into that. Now we're able to regularly produce digitally printed sensor arrays, printed circuit traces, down to maybe with unassisted, maybe in the 10 micron sort of feature size. Plastic logic, our trick was we were taking surface energy control and turning that process to define the gate of a transistor instead of limiting it 10 microns to bring it down to 1 micron or even down to 100 nanometer from a printed process. So and that's all about digital printing. One of the aspects, or the pros here, digital printing are drop on demand. We can print anything we want. Well, that's the most expensive way you could print something. Your inkjet printer per page is probably tens of cents per page, but you like it because at home you only print one of something and then you print something else. Or then when you want to print the newspaper, you don't use inkjet. You use other techniques. You use high throughput techniques, roll-based techniques. This is a gravure printer that was co-developed with a startup company that I helped found in Scotts Valley in Santa Cruz, California, doing roll printed OLEDs, flexible OLEDs for flexible displays. This is actually a gravure roll system made to go on flatbed for prototyping. And these involves essentially roll-to-roll compatible processing because they're role-based printing systems themselves. You essentially have a cylinder. This is called a gravure cylinder, and the gravure in Italian for engraved, essentially. And you engrave a pattern into a large metal cylinder. Those patterns can be engraved down to the sub-micron scale. Use a laser to engrave into this metal cylinder. Once you have that cylinder, it's an incredibly high resolution, incredibly rigid platform that can get to very high resolution, very high registration accuracy because it's solid. It's completely fixed. Then that gets coated with ink into those engraved pits, engraved into certain patterns. That ink gets metered off with this doctor blade, and then that gets rolled onto a substrate. And you can get very, very efficient, very, very high quality ink transfer. This works particularly well with more complicated solvent inks and more complicated inks. In inkjet, you have to engineer to be able to form these drops. Here you don't. There's a much wider process window for inks, and also much higher throughput. To give you an idea, this prints at how long does it take to get a page? To get a square meter would take you several minutes, okay, with typical inkjet. This runs happily at a meter per second. And in fact, it doesn't want to run slow. It wants to run fast. The kinetics and the fluid wetting and de-wetting processes actually run better the faster you go. So this runs at meters per second, very, very high throughput, very high quality. Example, there's cheap magazines and there's expensive ones. For many decades, I think in the US, the most premium, the highest quality printing ever done in the US was National Geographic. Pictures from National Geographic, it's all gravure. And that was their claim to fame because that's the highest quality graphic printing. What's the downside? We had to make that great big laser metal engraved cylinder. It can run millions, if not hundreds of millions of imprints, but it costs thousands of dollars to make every single one of those cylinders. If you're trying to print the newspaper every morning and you have to print 140 pages, you would have to make 140 gravure cylinders at 4 a.m. every morning. Very, very expensive process. So it's relatively expensive for design changes, but once you're up and running, a very, very high throughput process and a wide process window. And we've done that. Someone who's joining us in Washington done work showing gravure of things like printed biomaterials. We can print everything from proteins and DNA to OLED materials and demonstrate sort of printed light emitting diodes off of this printing technique.
Proteins, do you keep them alive?
Yeah, so that's the other thing. That's a good question. One of the issues is, actually you can inkjet print proteins in live, what were live cells. They tend not to survive because this is an extremely high shear process. There's a little piezoelectric driver that ejects these drops. And actually, the piezoelectric driver is constantly running at, say, 10 kilohertz, 30 kilohertz, this range, constantly, and it's almost about to eject the drop every time, and then whenever it needs to eject a drop, it gives it a slight extra boost. But what that means is that solution, it's basically like taking the solution and putting it in an ultrasound bath continuously, in a very, very high strength ultrasound bath. And so this tends to destroy, it'll even destroy things like carbon nanotubes, but organic molecules tend to get ripped apart in this process. This is actually, although much faster, a much gentler process, because the material that actually gets wicked into the wells here, you scrape off material, but the material that's in the well is never actually touched. And in a fluid dynamics sense, when you're in contact with a rigid surface, the velocity is zero at a wall. Now, it may move as you get further away, but it's essentially a very slow-moving fluid. The fluid is not moving. Everything else is moving really, really fast. So this is much more tolerant, much less shear, much lower shear process. So you're able to have viable biomaterials, whereas in inkjet, you might not be able to do that. This is a further example of more complex process integration of some of the kinds of things you can do with this sort of technology, where we've used that printer, the inkjet printer you saw in the previous stage to print maybe electrode traces. There's various encapsulation, oxygen plasma step, which is going to then pattern an additional blade coating deposition using wetting and de-wetting. The oxygen plasma through a mask locally produces very high wetting areas, and then the counter area is very de-wetting, and then you can literally scrape another ink across that of another material, and it will essentially completely de-wet off of the areas you don't want it, and only wet the areas that have been made hydrophobic by this oxygen plasma step, atmospheric step, not a vacuum step. And then you build up and actually can print additional hydrogel bumps onto this process. Sorry, the hydrogel is the wetting process, produces hydrogel bumps. This can be used this is an impedance sensor array. So this is an array of hydrogel sensors, and you're doing impedance measurements for wound characterization. So you can actually put it on a wound and actually do impedance mapping of the wound and look at magnitude and phase and correlate that with the damage threshold, and actually can sort of image wounds and image wound healing. Imagine a future printed flexible device. Not only would you be diagnostic, but you'd be therapeutic. You put it across the wound, but only part of the wound actually needs the medicine. And in fact, putting extra medicine can actually slow down the healing of the other parts or at different times. So in this way, you could actually sense the part that actually needs, say, for example, infection. Infection is a slightly different impedance signal, a slightly different temperature signal, and then you can actually locally release drugs just where you need it, and actually end up with a sort of combined, this is just the diagnostic part, but next generation would combine diagnostics and therapeutics. This also brings in the first concept of flexible electronics, fundamentally flexible. When do you need flexibility? Well, you need flexibility when you put something in a small space, but most importantly, you need flexibility when you start interacting with the human body. There's no part of the human body that's flat, and there's no part of the human body that it's comfortable to have something that's not flexible in contact with it for very long. So we start thinking about integrated systems, how we bring all these components together, say sensors, but maybe what I showed you before was an example of a sensor, but it had a bunch of leads coming out too that has to be plugged into some sort of reader or some other type of electronics. We start looking forward to completely autonomous medical sensors. Imagine distributing, say, medical sensors, tropical disease sensors in the third world. There's, one of the issues with some of these outbreaks is they have to go get samples, which is dangerous. They have to take those samples and they have to ship them back, in a plane, across continents to a lab where they can do the analysis. That adds extra, weeks of delay. It adds extra cost, extra complexity. If instead you actually had a diagnostic, say maybe a DNA-based diagnostic card, if it could read itself, very low cost, doesn't require any external reader. Another example, very interesting device, and Seattle's been part of this, is imagine future glucosameters. I think we'll look back 50 years from now and look back at, a very large fraction of the population is already diabetic, and more will be. And the fact that you used to actually take and stick yourself and bleed, 5 times a day to test your blood, I think it will seem barbaric to us 50 years from now that you would actually do that. Think about all the infection, it's just crazy. But it's a very difficult problem. Imagine if instead you had a test, you had a sweat-based sensor or the fluid of your eye-based sensor locally Say, imagine the optical glucosometer. You can actually detect glucose level based on, the water in your eye, different chemical balance in the water in your eye. Basically a glucosometer contact lens. How are you going to power that? How are you going to drive those electronics? People talk about wireless. Are you going to put, an RF horn up to your face and charge your body? Not very popular. Are you going to put a rigid lithium battery, which is a neurologically active and toxic substance, on the surface of your eye in the body fluid? Not very likely. So we're thinking now about how do we fully integrate systems, not just the sensor, maybe flexible displays, but also how do we power it? And how do we do the wireless connectivity? And if you saw before, we talked about the Flexible Hybrid Electronics Center. That's funded from the federal government through the Air Force Research Lab. The Air Force Research Lab wants this yesterday. They want to monitor pilots. There's something like tens of thousands of sensors on a Raptor fighter aircraft. It's $1 billion plane. There's 0 sensors on the pilot. Every single pilot is 28 years old. Pilots never, ever, ever refuse to fly. They love to fly. They want to fly. If you ask them, are you ready to fly? They say yes. Doesn't matter. They could be near death. They could be hungover for a week. Doesn't matter. They'll fly. You're going to put them in control of a $1 billion piece of aircraft that could, rain hellfire on 1 million people in one shot. So they like to monitor the pilot. They want health sensors and performance monitoring sensors to actually go on the pilot to know if they're ready to fly, and then, of course, to know that they're okay while they're flying. Because the printed electronics and transistors are not fast enough right now to do things like efficient RF transmission, we need to hybridize that. We got to use silicon CMOS today. So we have to take silicon CMOS, we have to thin it down, maybe sub 10 microns, get it flexible, and then integrate that with the rest of these flexible devices, say to go into sort of a hybrid flexible performance monitoring system. That's one of the missions of this flexible hybrid electronic system we're involved in. There's a lot of answers here. What's the most important part? I'm biased, but I started a company to do it. The most important part of this system, what's the most important part of this system? My smartphone, what's the most important part of this system? What's the most important problem with this? It's the battery. It's time. You can pack a huge amount of functionality in here, but it's always this great big soap brick is because you got to have a big enough battery to do all this stuff. Energy. And whenever you start talking about ultra-thin devices, they're going to be flexible enough. They need to be 100 microns thin to really be fully conformal in clothing on the body. The energy density plummets, and so energy, you're starved for energy. So battery is very important. So we started Imprint Energy as a printed flexible battery company, both to exploit some of the special chemistry, printable chemistry of zinc that is safe, non-toxic, and low reactivity, so we can handle it in air. That's good because we don't need to package it so much, so we can make it thinner. It's also good because now we can print it, we can process it in air. We can use screen printing processes to print these batteries, and now we can print them as flexible devices, ultra-thin, a couple 100 micron thick devices onto foils and make them very, very thin. And kind of applications, you think about the basic system. What are the essential components? Sensing, information display, logic, memory, but connectivity drives all these things. And we start thinking about interacting with the human body. You have another special set of constraints. Low toxicity. Companies like, I'll mention their name because I'm not in NDA anymore, Duracell. Duracell didn't make lithium batteries. They completely stayed out of that. There's one reason why, because they make a huge amount of money selling zinc manganese batteries, disposable batteries. But there's another reason, because at the time, the biggest market, target market was really lithium coin cells. And lithium coin cells, you don't hear about it much. They're already banned in California and other places in things like audio cards and things like that, and toys. You ever notice now when you buy a toy, even the charged toys, and you have to, on Christmas, you ever notice they all have a screw on them now? You have to break out the screwdriver to open them up. Like, whatever happened to the good old days of the quarter or the pop-up? The reason why is because it kills kids. Because a coin cell, lithium coin cell, a kid swallows a lithium coin cell, it gets stuck in their esophagus, and you have this hydroxide reaction and burns a hole in their esophagus. And once it happens, they can't stop it. So there's a very high mortality rate. Duracell very early on decided they would not go in. They had knew that 10 years ago, and they said as a company decision they would not go into that business because of it was related to mortality in kids. So toxicity is a big issue, especially as we start talking about powering smaller and smaller devices, smaller and smaller things that can end up in harm's way. things that are going to get banged, going to get knocked. We can't afford to have lithium fires. Things that are going to leak directly onto the human skin, things that are going to end up in your 30-year-old's mouth and he's going to be chewing on it. All these sort of things are going to happen as we start integrating electronics into everything from packaging, smart packaging, Internet of Things packaging, to smart Band-Aids, to glucoximeters and direct on-body devices. And again, other important things, thinness and flexibility, both in terms of cost, conformal integration, but also in terms of comfort. And I don't know if it's lastly here, but also sustainability in terms of a full life cycle. We start talking about medical devices, packaging. We want to put FedEx. FedEx already got into the RFID business, but they'd really like to be in the Wi-Fi or Bluetooth business because they don't want to have to install these RFID readers. Everyone already has a Bluetooth and a Wi-Fi reader in their pocket in every car and every building everywhere. If you could put a 10-cent Wi-Fi tag on every FedEx package, you would know when your package came in the building. You would know where it was everywhere in the supply chain. But it has to be disposable. They don't want to have to rip it up and recycle it. You can't dispose lithium batteries. It's also transporting a large amount of lithium batteries is a hazardous materials transport. So that also drove our decision to explore the printable zinc system at Imprint Energy. Kind of accelerate, but basically it's a 5-layer device built around this custom, this ionic liquid, sort of a novel replacement of a lot of the problem with the lithium cell is you have the toxicity of lithium, but you also have lithium is pyrophoric. It reacts with air. It has that silver bag that's now black because they put black polyimide around it. You still silver underneath the black stuff in your iPhone battery or whatever, your Samsung battery. That bag is to keep water and moisture out and to keep lithium in. If water and moisture got in fast enough, it would start to smolder. So you have a spark, but you also have fuel. The electrolyte of a lithium battery is an organic solvent. It's not that far from gasoline. Literally, it's a highly flammable solvent. So you got spark and you got fuel. That's a difficult combination. By moving to the zinc system, we take away from the spark. It's not pyrophoric, it's air stable. But also we use these highly stable ionic liquid electrolytes that are essentially inflammable and very low volatility. They have no volatility and they're very, very low flammability. And we have to do special things to make them high enough ionic conductivity, but we're also assisted by the fact that we're printing this as ultra-thin film, so the transport distances are very, very small. In this way, through starting with sort of highly engineered materials, very scalable printed processes, including sheet-based printing, but also roll-to-roll printing. We're currently doing roll-to-roll scale-up in Sweden right now. We can produce in high volume, relatively low cost, high energy density, flexible batteries. Let's see. And one of the examples of the proofs of concept of doing this is actually to demonstrate on a 12.5 micron nickel substrate, to give you an idea how flexible 12.5 micron metal foil is. Aluminum foil is like 50 or 100 microns. You already know how flexible it is. Extremely flexible, extremely thin. We're able to demonstrate thin film batteries out of, I think, about 5 square centimeters of battery with enough power to directly drive a Bluetooth. This is a Bluetooth sort of handshaking. It's the power demand at the battery side from a direct coupled Bluetooth wake up and a sort of preamble and Bluetooth communication. And it looks like nothing, you guys who work on microprocessors think this is a joke, 45 milliwatts. For a very, very small battery, even a coin cell, this is very, very difficult to deliver this sort of instantaneous power. But we were, through this sort of high surface area nano-based printed cells, we're able to get actually very high discharge rates and good power density, enough to demonstrate wireless connectivity. And we built various flexible devices and prototypes off of that. And ultimately, the story comparing this to a lithium battery, this is energy density versus cell thickness. The actual energy density that you see advertised for your Samsung Galaxies and iPhones is up here in the 400 watt-hours per liter or 400 milliwatt-hours per cubic centimeter. But as they get thinner, it drops off dramatically. The reason why is packaging. Because you have to, regardless of the cell, you still have to prevent the air, water, and moisture from getting in. And in fact, the smaller the cell is, the higher the surface to volume is. So the more packaging per unit volume you need. And as you get very thin, you actually end up with no space for battery anymore. As these cell walls, this packaging is hundreds of microns thick. If you want to make a flexible cell, you need to be hundreds of microns thick. You have nothing but packaging. There's no space for lithium anymore. There's no active material space. So actually, the energy density of these things we're talking about for flexible electronics, the energy density is very, very low. When we move to the zinc system, we can already exceed today what they're doing in lithium polymer. And it's largely about the stability. I mean, there's a lot of smart engineering of all these materials, but it's largely about that packaging constraint. Because we're using printable, air-safe materials, we don't need 200 microns of packaging on either side. We need 50 microns of packaging because it's already air-stable. It's not that moisture sensitive. And so overall, we can get in the same very thin device a lot more active material per unit thickness of device, so we can get a lot more energy. So now I'll sort of segue into, hopefully this works, just the last couple of minutes, a little bit, I'll have to do it manually. I'll say a little bit about the activity at University of Washington and the lab I'm building. And I hope you can stay because this is my self-serving interest to get you interested in what is happening. Okay, that's my lovely son. Go through the song and dance. Now you can see what I can see. So Clean Energy Institute, you saw I was the Washington Research Professor of Clean Energy. It comes from the Clean Energy Institute, which really comes from the governor in promoting energy economy in the state of Washington. You may or may not know, but University of Washington is a net producer of energy through hydroelectric power, and Pacific Northwest National Lab is one of the world recognized in sort of grid storage technology, or one of the world leaders in that area. And now we're talking about, with all the advanced materials, chemistry, nanochemistry, University of Washington, trying to take that and push that and bridge the gap between sort of fundamental early stage physics and material science into advanced manufacturing to actually make it impactful. And so the governor has actually been funding laboratory. He funded hiring me, and the Washington Research Foundation funded hiring me, someone who sort of straddles both worlds, the industrial entrepreneurial world of trying to make things really work, all the way back to the academic world of University of Cambridge and physics and electronics. So I can sit in both and help from this process of going from sort of fundamental early stage device physics and materials through to larger scale device prototyping, try to realize, the only reason, of course, there are physicists who disagree, they're interested in the physics of this, and in my heart, I'm a physicist too, but the real reason why these materials are interesting is because how you can make them. So they're only interesting if they can be scaled and impactful. They're otherwise not interesting. The world, we can already make a 45% efficient solar cell. Spectralab, owned by Boeing, makes these solar cells and they go on satellites. They're, I don't know, tens of thousands of dollars per square meter. Far too expensive, but the physics, it's already known how to make almost a perfect solar cell. The problem is you can't make it cheaply enough. So in terms of new solar materials, new energy materials, it's not the fundamental, can it be done? It's how you can do it. Can you do it in a scalable, sustainable way? So my lab and the new efforts are all about translating from molecules to bench scale and even going to pilot scale ultra-raw processing. And we're doing that. And this is my lab we're building up. We call it the Speed Lab, Scalable Printed Electronics and Energy Devices Lab, where we have everything. We are building, certainly in university sense, and I think probably the US's largest research roll-to-roll system, and maybe in the world. It's being custom built for us in Denmark. And these are some of the prototype systems been used to produce things like semi-transparent large area flexible solar arrays and things of that sort. We also have capabilities to do all sorts of rapid prototyping and flexible and printed electronics, of course, printed batteries, energy devices, but also things like printed sensor arrays and other things for flexible and conformal electronics. And this fits into the Washington Clean Energy Test Beds, which is a further investment. The governor was really excited that we started this program, and so excited and so interested in getting reelected and making energy a platform, a plank of his platform, that he further invested in this concept of scaling from academia to industry in the Pacific Northwest. So he started this Clean Energy Test Beds. And Jihui Yang and I, Jihui is from GE, Electric Vehicle Division. He's a new hire, relatively new hire, University of Washington, so very industry experience in the battery space. And then I come from printed electronics industrial research, to lead the scale-up and characterization test bed, where we're looking at translating both from the academic side to larger scale, but also having a hardware and equipment so that companies can come in, solar industry, large-scale battery industry can come in and characterize batteries, do environmental testing, do module testing, light soaking, to characterize and calibrate their modules, and sort of collaborate with the university researchers to try to foster more entrepreneurial, more energy industry development in the Seattle area and the Pacific Northwest area. We're right now building a lab. This is the Bowman building. This is, if you know University Village, if we jumped out of the back of this, we would jump into the back parking lot. It would be quite a drop. But you jump into the back parking lot of the University Village. This is right behind University Village, called the Bowman building. It's a huge shell, like 20-foot high ceiling shell, half of which this part over here is being used by the Aeronautical Engineering Department to fly drones around inside. We're going to take that space and build sort of a semi-clean print lab in a shell inside a shell, build a lab inside there as our temporary lab. And this is about a 4,500 square feet facility with everything from roll-to-roll coating, sheet-based coating, through to solar module testing, large-scale panel testing, large-scale battery testing, with the idea of kind of crossing over and bringing in industrial partners to do industrial research along with the academic research. And we'll have an extensive array of deposition tools, but also characterization tools. There's all the characterization we'll have. A lot of times that's what industry doesn't have. You know, they have something to make it, but they don't have the $1 million electron microscope or special chromatography system, but the university does. So we're coupling all the characterization and sort of electrical test equipment also with the analytical equipment in the university. Things like, oops, sorry, didn't go there, sorry. Well, we had the molecular analysis facility which has extensive analytical capabilities. And so for industrial partners working in the lab, they also can get access to all the analytical capabilities across the university in molecular analysis and device fabrication. And we're also coupled closely with the WNF, which is the Washington Nanofabrication Facility. So we also have the ability to go and hybridize and go back and forth between new printed electronics and thin silicon, looking at new printed nanomaterials and combine that with traditional vacuum and deposited wafer-based silicon in the Washington Nanofabrication Facility, which is at Fluke Hall on campus and has world-class semiconductor processing tools. They get used by Intel and Micron and people like that. So I guess with that, we'll wrap up. And I hope, part of my mission in coming here is to for me to come see what Microsoft is about and see what it's like over here. And get a chance to tell you about the exciting work we're doing, but also, seed ideas about how we could start to work together and how we could start to bring local industry into these translational laboratories we're building on campus in this new print electronics area. So, thank you very much.
We take some questions.
Mentioned you like to bring local industry in. What kind of procedures or how do you charge?
However we can. So that's a good question. Another good question. So right now we're looking at multiple models. There's a fee-based model, and that's true in the Washington Nanofabrication at WNF and in the analytical facility. There's a certain amount of time per hour on a particular instrument. So you literally sign up, you pay it's relative, it's quite inexpensive actually compared to actually having to maintain the tool. It's heavily subsidized, but you pay that an hourly rate for how much you use an instrument, and there might be a technician or some sort of staff support rate. If you need someone else to run it for you or help support you, there's some sort of fee. But we're also looking at joint programs where you can become a member of the center and or fund maybe shared research where there might be some support on the academic side, and then that academic side is doing research that you're interested in or supporting your project. So we're working out those mechanisms. In fact, one of the surprising things, I've worked in the University of California system, I've worked in the University of Cambridge system, I worked in the Massachusetts Institute of Technology Intellectual Property situation. I can say University of Washington is the most flexible I've ever seen. It's a very good thing. So there's not a lot of strict absolutes. The university, the governor wants this to happen. The university wants it to happen. So we're pretty flexible. But right now it's fee-based, but we're also looking at projects and having an example case would be a very large aeronautics manufacturer, remain unnamed. There's a potential that we would actually bring some of their equipment into the lab. They would become a partner. They would provide some investment, but then they would actually literally place some of their tools in our lab, and they would use a combination of our tools and their tools, and then they would have access. So there's all kinds, every kind of possible. Right now, nothing's not possible.
I didn't catch you. You mentioned the clean energy. What kind of product do you have on the clean energy?
Well, that's the primary focus for hiring me was on energy-related devices. So we're looking at alternative. We didn't talk enough about the solar cells and the physics of solar cells, but we're looking at very low carbon footprint manufacturing of solar cells. That's the primary driver for that roll-to-roll printing, is it would actually be roll-to-roll processing high-efficiency solar cells. That's where I started in University of Cambridge, was actually organic solar cells. At that time, organic solar cells were about 2% efficiency, and we made, at the time, the world's highest efficiency solution process solar cell ever made, and that was 2%. Today, we're talking about solution process solar cells that are 20%. And it's 10x, it took 10 years, whatever. But that's actually quite significant because that now exceeds or matches or exceeds silicon modules. So now you're talking about printable, low carbon footprint to manufacture, low temperature process solar. So that's clean energy. The other aspect of clean energy is looking at things like grid storage to be more efficient, but also non-lithium batteries, looking at less environmentally damaging battery systems. And so zinc-based battery systems, aluminum air-based battery systems.
So what is the state of the art? I mean, how dense you can print the surface? I mean,
well, it's not that dense. And actually, one of the strengths and one of the hybridization is actually the real focus. The biggest strength of the technology is actually where you need to do large area. So we actually, we can do stuff. We can make features. So we're working on one of the interesting things in solar. So we work with an unnamed solar company, may become a partner of the center. We're doing nanophotonic patterning of essentially anti-reflection coatings and anti-fouling coatings for solar cells. They're not interested in making the cells better anymore. They're like, the cells are almost theoretically to their maximum efficiency. We could spend hundreds of millions in research and we might improve the cell efficiency by another couple tenths of a percent. We can put 100x less investment into looking at anti-reflection coatings that can be made with the right characteristics in 25-year lifetime that can increase the cell efficiency by 2 and 3%. So in those cases, we're doing nanoscale fabrication. We're talking about features, 100 nanometer scale features. But those are passive devices, just simply photonic coatings. They have a special two-dimensional, like a moth eye type structure for anti-reflection and super hydrophobicity. Essentially, water can't wet it. The curvature is so high. But in terms of devices, typically there's some features you can get into the sub-micron, but we're typically talking about micron scale features. But really where it shines is not that. That's where the hybrid comes in. If you need to do a Bluetooth, low power Bluetooth, 5 milliwatt peak Bluetooth, you need silicon right now. So instead, we don't try to do that, but we do the other things. Flexible antennas, we do the batteries, flexible large area batteries. Sensors, typically sensor signal depends on the area of the sensor. Per unit area, silicon very, very expensive. But we can actually make large area sensors, optical sensors, biosensors, and large area printing. So I'm always trying to push it the other way. Let's look at the big devices, because those are the ones that are big. Those are the ones that have to be flexible, and that's what we're better at.
Waterproof.
Well, sometimes they have water in them, so they are one with the water. That's a good question. One of the biggest issues with the photovoltaics is how do you get it to last for 25 years? 25 years is a really, really long time. You think about something sitting on the roof, lots of UV, lots of moisture. What's going to happen? Well, there's lots of water. It's going to fall on it, hail, snow. Algae is going to grow on it. Fungus is going to grow on it. Birds are going to poop on it. All kinds of 25 years is a very long time. So barrier films and robustness of barrier films that are compatible, flexible is a big development area. Luckily, part of that has been part of that bleeding edge has already been blunted by the OLED. So you've seen flexible OLEDs come about. OLEDs have they have a much higher local intensity of excitation, but for a shorter lifetime. Your OLED for a flexible phone needs to last like 2 years. I want you to buy a new phone every 2 years at max. Apple would prefer every 1 year. But it's a much higher excitation density than a solar cell. But they've managed to push that out and develop barrier films on flex that are getting there. But that's an active area. That's something like industrial partnerships with, say, 3M and people like that are of strong interest to kind of be able to do that, to get those sort of scalable barrier films and adhesives for solar. And when you can't keep it out, then you live with it. So we're also looking at sort of molecular routes to fixing that water, preventing it from reacting with other parts of the device so we can stabilize devices that way. That's a good question. So sometimes it doesn't matter. The batteries, we try to make them moisture intolerant. But in the solar cell case, we got to keep the moisture out or trap it before it does something bad. And it has to be for 25 years. It's a really long time.
I was thinking of something that wouldn't be such a long time, but much deeper. I'm an ocean engineer.
Okay.
So 500-600 meters.
Well, hydrostatic pressure, it depends on the type of device. There's not like free volume. Actually, we try to, usually that's a bad thing, so we try to get rid of that. So they're still incompressible.
I was thinking that it's not very compressible.
So I can't, there's always tricks. There's always problems when you come down to it, but fundamentally, I don't think that's a big limitation in terms of just sheer pressure. Some actually good things happen in batteries. Good things happen in pressure, usually.
So the type of batteries that you concentrate on are rechargeable batteries or?
Both. So interestingly enough, the big milestone in the zinc polymer case was that we were able to get rechargeability out of zinc. Zinc and lithium metal. You don't see a lithium metal battery. You ever talk to, I don't know if you're into the space here, but there's silicon, anode silicon, nanosilicon in batteries. People talk about it for Teslas, and it hasn't actually happened. That's because they can't actually use pure lithium metal because it's so reactive. Sony tried about a decade ago, and Sony almost lost everything because of failures of lithium metal batteries and fires related to them. So they don't actually use pure lithium metal. We can use pures, and there's a couple reasons. One, because it's so reactive, but also when you cycle it, you charge and discharge it. When the lithium metal gets plated back to its source, when you recharge the battery, it doesn't just go flat in a planar film. It builds a three-dimensional structure, a dendritic structure, and those grow each cycle, and it gets closer. And the ones, as it grows, it accelerates. The part that's closest to the next electrode goes faster, and it shorts across the battery and leads to a fire. Because of that electrolyte, that ionic liquid polymer electrolyte in the zinc, we're able to sort of suppress that dendrite formation in zinc, which has limited rechargeability in zinc before. So that's part of the trick. So we went out with the big offering that we could get rechargeability out of zinc. It turns out the most exciting initial customers all want single-use batteries because they want medical devices and things like that, which are going to get contaminated. They're either single-use or limited recharge. So typically anything that goes on the body is not going to be there for more than a few days because the adhesive is actually sticking to your skin cells, and your skin cells are getting shed. It's going to come off. It's going to get contaminated. You can't really sterilize the rest of the electronics. It'll destroy the electronics anyway, and it's too expensive to sterilize anything anyway. No one wants to use a reused thing from someone else anymore. So it needs to be disposable. So it might need to be charged if it's a daily use, maybe 3 days, maybe less than 10 charge cycles, and sometimes 1. But it needs to be incineratable, and it needs to be non-toxic and all those things. So we went out with rechargeability, but actually a big driver has been single use. Sorry, there's a question in the back.
I was just wondering, are you doing anything with processing the power with very thin electronics? No.
Well, through the Flexible Hydroelectronics Center and with the work with my battery company, we partnered with people like American Semiconductor doing ultra-thin silicon microcontrollers. So they're developing processes for that. So in our sense, we don't, right now in this lab, we're not focusing a lot on trying to make really highly integrated logic. But we do work with the thin silicon side. And there are designs, it's not just as trivial as let's just take the silicon circuit and thin it back. that there are tricks in that process, things you can and can't do. So there are partners, and we'd be certainly interested in working with other people who are thinking about, large-scale integration in silicon that can be thinned.
Yeah, I'm not talking about processing like data processing. I'm talking about power processing. Taking the power from these little thin batteries or whatever and converting it to the right voltage so that some other device can use it.
That's definitely interesting. So one of the things you fight is convention. So convention, people have lived with lithium batteries, 3.7 volts for a decade now. And so these systems are designed to run off 3.7 volts when they don't actually need it. And so we always, a lot of times when we're developing these new applications, we have to build up battery stacks, multi-series stacks, so we can get to 3.7 volts. And we find out that they're then down converting it back down to like 1 volt to drive the logic. And so we obviously want to cut right through that layer and drive direct, be more efficient. Things that, types of cells, some of the types of designs like step-up converters, even very, very good engineers from some of the best wireless companies in the world, they think, oh yeah, I just need a peak of milliwatts or 10 milliwatts or something. Well, it turns out if you actually put it on a scope and you look on the microsecond scale, there are huge power pulses that kind of need to bootstrap these circuits and get them started. And they just, they don't really care about it because their circuits always run, so they never worry about it. We worry about that. So we've had a lot of, there can be issues based on conventional approaches that assume certain peak power draws that can't be had from these thin structures. So really efficient voltage converters and things like that are pretty interesting. And that's been an issue for us. One example is driving a super high power like Wi-Fi burst radio. It needs really large instantaneous power, watt, something like that. But the way to do it, to run it off a tiny battery, is you also use a supercapacitor, but you still need to charge up that supercapacitor. And some of those conventional circuits to do that have these immensely high inrush currents. And initially, when the very first sinusoid is really, really low voltage, really, really high inrush current, that can actually short the battery. And when the battery voltage drops so low, then the circuit doesn't latch up and they don't operate. So we've run into those kind of problems and try to design out or get partners to design out sort of ones that are, power circuits that are tuned to these technologies. So on a case by case, but it's an interesting issue. It can be significant.
I have one last question before the XCOM meets. Any questions?
How large of modules can you test?
So we are basing the system. It depends on which test you need. So we're able to fabricate. There's nothing in the new facility that won't do less than 300 millimeter, 12 inch. So every tool will do 12 inch or bigger. In some cases, we're like this is a light soaking. This is huge. So this is for a full size light soaking panel. So there's a huge solar simulator source or UV source here, and you can put panels on either side. And that's I should know the number, but that's a standard size solar panel arrays, and there's a couple like 3 foot by 6. So
that does a wide spectrum.
That does a wide spectrum. There's various degrees of solar simulation. It's actually really hard to simulate the sun exactly for the synthetic source, and there's various qualities. This would be like what they call like a single A solar simulator that matches the spectrum to a certain percentage loss. For the 300 miller, we have a triple A, which is the best you can get, the closest match you can really spec a match to solar spectrum. But this is still pretty good. This is industry standard for doing large module light soaking. There's also UV. There's also UV lamp.
How low wavelength does it go down to?
The AAA one is out to 1200 nanometer, which is pretty far. The AA probably it's not going to, maybe 800 or something would be the farthest it would go. That's really important, especially when you're talking about new solar technologies, because a lot of things can happen out at these fringes that you don't normally see in silicon, like silicon's 1.1 EV band gap. You don't see anything. You don't worry about UV and stuff so much, and you don't worry about deep IR stuff. Some of these organics, there might be additional power that you can actually harvest out of there that's in sunlight that the test is not seeing. On the other end, there could be additional damage that can be happening on the near UV end that silicon doesn't care about and the standard test doesn't get. So we're definitely sensitive to that. So we're getting the highest specification, broadest band solar simulation we can. There's an interesting question about NREL certification. So if NREL is a National Renewable Energy Laboratory, they are the de facto standard for solar testing. Whenever you have a new solar cell and you want to claim, that it's 18.3% efficient, the only time you believe it is when you get NREL certified. And so we're planning to have our system calibrated to NREL standard and have it cross-calibrated for cells, and then potentially a module will actually have it certified. So certify that this test will adhere to the standard, NREL standard for testing modules. We haven't done that yet, but that's our intention, is to actually get NREL certification for the module, the big one, and then sort of NREL sort of cross-reference the cell-based one.
Okay, so with that, let's thank Devin for the exciting talk.
Thank you.
So Devin and I can wait outside.